Hello everyone, my name is Claure. I am a PhD student in mechanical engineering at Cornell University. I'm advised by Dr. Malte Jung, and this work was done in collaboration with Dr. Stefanos Nikolaidis at the University of Southern California. A common paradigm in human-robot collaboration often sees one robot and one human working together to accomplish some sort of task. Now, the role of the robot is often to allocate some sort of resource or tool to its human counterpart with the idea that this would facilitate the process for the human. But what happens when we introduce multiple individuals into the robot's environment? Now the robot has to make a decision of whom to allocate its resource to. And this decision is not an easy one, as research in psychology has shown us that humans are in fact attuned to how resources are distributed amongst team members. So how a robot distributes its resources amongst team members could in fact influence the team's dynamic, which would influence the team's overall performance. This raises a larger question that we aim to tackle with this project, which is, how should a robot allocate resources amongst team members? We look at this problem through the lens of the multi-armed bandit framework, which can be visualized as follows. A gambler walks into a casino that is filled with slot machines. Each of these slot machines has their own independent and identically distributed reward distribution, which the gambler is unaware of. Given that the gambler's goal is to maximize his or her overall profit, the gambler is now faced with the exploration versus exploitation dilemma, where the gambler can allocate more resources into exploring the different slot machines and learning about their distributions, or the gambler can allocate more resources into exploiting the slot machine which has previously given him or her the highest reward. Now, this sort of framework has been applied in a large number of contexts, from ad selection to clinical trials to network routing, and more recently has been applied in the field of human-robot interaction. Now, we frame our problem as follows, and we use a toy example to help explain it more clearly. We have a team of individuals, here denoted as I equals 1, I equals 2, and I equals 3. Each of these individuals has their own independent and identically distributed reward distribution, which is unknown to the robot. Now, the robot at each turn selects one individual and receives a normalized reward from their distribution. Also, what is unknown to the robot is which one of these team members is the best performing individual or the individual with the highest level of experience. Oftentimes, we look to minimize regret, where regret is defined as the loss that is incurred from selecting a suboptimal action. A common solution to the multi-armed bandit framework is known as the upper confidence bound, or the UCB, where the algorithm at each turn calculates a UCB value for every individual. Now, the UCB value is calculated by summing the average reward that the individual has incurred so far with a confidence interval. And from there, the algorithm selects the individual with the highest UCB value. From our simulation, you can see that the algorithm is able to accurately select and identify the best performing individual, which is I equals 2. But what we can see as well is that this individual is selected a disproportionate number of times. As I have mentioned before, individuals within a team are sensitive to how resources are distributed amongst team members, so we can safely assume that this distribution would be seen as unfair by various team members. So we introduced the strict rate constrained UCB, where we guarantee that the pulling rate at any time for each individual is at least V minus epsilon, where V is the minimum pulling rate. This is done through the algorithm, which divides the overall time steps into blocks of length 1 over V and fixes certain time slots where it selects pre-scheduled individuals. Given our regret definition for our strict rate constrained UCB, we are able to prove that the regret bound is close to the original unconstrained UCB. Looking at our simulation, we can also see that lower performing individuals are selected more often than in this condition than in the unconstrained UCB. We are operating under the assumption that selecting the best performing individual is beneficial to the team's overall output. We deployed our algorithm in our developed Tetris platform, which allowed two individuals to work together to try to obtain the largest Tetris score. The reason we use Tetris is because it has been applied in a large number of research fields, from artificial intelligence to psychology. Additionally, it let us explore the team dynamics of each team by allowing us to look into their individual performance across time as well as the team's overall performance. We used Amazon Mechanical Turk to recruit participants from the United States and pair them in teams of 2, where these teams were placed into one of 3 different conditions where we manipulated or altered the minimum pulling rate. Across each condition, the gameplay was very similar. Only one individual had access to the following Tetris pieces per turn, where one turn consisted of 7 individual consecutive Tetris pieces. Now, the system running our algorithm decided which individual would have access to these following pieces per turn. In the UCB 50% condition, the algorithm gave an equal number of turns to both the weaker performing individuals and the stronger performing individuals of each team. In the UCB 33% condition, due to the fact that we altered the minimum pulling rate, the algorithm selected the stronger performing individuals slightly more times than the lower performing individual. In the UCB 25% condition, the algorithm selected the stronger performing individual more times than the lower performing individual. In this condition, the stronger performing individual was selected more times than in the 33% condition. To analyze performance and responses, we grouped the stronger performing individuals of each team as well as the weaker performing individuals. Looking at their performance, we saw no statistically significant differences across conditions. Looking at the subjective responses, we see a significant difference between the weak and the strong players in their perception of fairness in the least fair condition, which was the UCB 25% condition, and that reducing the minimum rate from 33% to 25% showed a negative effect on the trust of weak players. In conclusion, we present a multi-arm bandit variant algorithm capable of maintaining a level of fairness by administering a minimum rate constraint limiting the number of times an individual may be assigned to a resource. We then deployed the algorithm on a developed Tetris platform where results from this user study suggest that allocating more resources towards one individual negatively influences the trust of weaker players towards the system. For a full set of results and analysis, we point readers to our paper. I would like to conclude by thanking my collaborators, as well as my advisors, Dr. Malte, Jung, and Dr. Stefanos Nikolaidis, for all their continued support throughout this project. I would also urge viewers to send any questions that they may have to one of us regarding our paper. Thank you so much for your time.